Good morning, everybody, and welcome to our distinguished seminar today. As part of our Energy Institute Distinguished Seminar Series. It is a great pleasure for me to introduce Professor Michael Baldea from the University of Texas at Austin. Actually, Michael, just as a parenthesis, is somewhat linked also to Texas A&M from his academic tree, that is, because he is the academic grandchild of Professor Kostas Kravouris, our own Kostas Kravouris. So and interestingly, he has a Greek route as well, hidden through his Romanian blood, because both his academic grandfather and academic father, they are both Greek professors, Professor Dautidis, where he did his PhD at the University of Minnesota. Now he has his own distinguished career over the years, and now he holds the Henry Beckman Professorship in the department, in the Maketa, of course, Department of Chemical Engineering at UT, where he's also a core faculty member in the Oden Institute for Computational Engineering and Sciences there. He did his undergraduate and master degrees in chemical engineering at the largest university in Romania, located at the city of Cluj-Napoca, at the Babeș-Bolyai University there. And then he joined for his PhD at the University of Minnesota, where he worked with Professor Prodromos Dautidis. Before entering academia, he also had an industrial career, having joined Praxair, which is now part of the Libre technology group, and he was based in New York in the town of Tonawanda. He has received several awards, including the ISS Institute Award for Excellence in Industrial Gases Technology. In his younger eras, also he got the Outstanding Young Researcher Award from the Computer Systems Technology Division of ISSC, and certainly he will be a strong candidate in the years to come for the actual computing award. He got the NSF Career Award, the Moncrief Grand Challenge Award, the ACS Doctoral New Investigator Award, and the Model-Based Innovation Prize for Process Systems Engineering. This is an award twice, in fact, and I know personally because I was the chair of the committee selecting the awardees. So, I have always appreciated the depth of his research, great quality of his research in the areas of dynamics, optimization, and control of process and energy systems. He is an executive editor for Industrial and Engineering Chemistry Research, a journal that all of us submit, and he is the Chief Technology Officer of the newest Manufacturing USA Institute, EPICS, related to electrification for the process industry. So with that, it is my great pleasure, and join me in warmly welcoming Professor Michael Baldea, and he's going to touch upon an issue that I think is very kind of contemporary, asking the question, can machine learning produce actual learning? So please welcome Professor Michael Baldea.
Thank you, Sarah, for your introduction. Thank you all for being here. It's great to be here. It's been a while since I've been at A&M, but it's a great and easy trip to make. I'm happy to share with you some of the work that we did. So to begin, I want to give credit to a few folks who are essential to generating the results that I will present today. So Fernando Lajarza is a graduate student in my group, and he's now working for Meta, so Facebook, Instagram. And then Elsa, who's a very perseverant student in the group of Professor Rogov at Northwestern. And so the collaboration with their group will be highlighted in kind of second part of their talk. And I'll discuss some applications of the concept of all these. So let me start with an old story. And we're going to talk about chemical reactions. I don't know if you're all familiar with someone called Alfred J. Lotka. He was a physical chemist. And he lived in an olden time when concerns about the practicality of your thoughts were somewhat reduced compared to today. And his question, or what he was wondering about, is if he were to write a material balance on a fairly simple system where one component went to, so A went to B, B went to C, but then he started asking the question, well, what if B went back to A? And we wrote this kind of periodic reaction system. What would happen? So he said there's no reaction known to man that actually followed this above law. And as a matter of fact, he was motivated by concepts that lied outside of physical chemistry. So he wrote these material balances. He explored a little bit the periodic reactions. We're talking more than 100 years ago now. And this didn't look too much at the time. However, back on the continent, so across the Atlantic, there was another individual, this time a mathematician. His name was Vito Volterra. And he was having this conversation about, this is 1927 now, so this post-World War I. He was having this discussion about the increasing number of predatory fish in the Adriatic. And this is post-World War. There was a drop in fishing because the economy was also messed up. So this is something that was brought up in a conversation by his future son-in-law. So if you want to woo your father-in-law, this is definitely a conversation that you want to have. So clearly this is a very fun guy who knew exactly what to talk at dinner. So, but Vito Volterra, being Vito Volterra, took that to heart. And he says in his book, which became kind of a classic in mathematical biology, he says, let's say we have two species and then one of them feeds upon each other. And how do we model something like this? And it turns out that the equation is a system of two nonlinear differential equations. And you can see that there's these cross terms, right, where unfortunately,
It doesn't
work on the screen. Yeah. It's okay.
But you can solve it.
I can try to do it with the arrow. So you can see that there's these cross terms, right? That's the nonlinear part where the concentration of one of the species is multiplied by the other in each of the rate laws here. So this all already starts to look suspiciously like the Lotka model. And the Lotka model does have an extra term, but that's not super relevant. Fundamentally, these two are kind of the same. So what eventually came of this work, seemingly disparate efforts, is something called the Lotka-Volterra dynamic. So if you ever took a class in nonlinear systems, if you ever took a class in chaos and dynamical systems, if you probably looked at numerical methods, or if you do anything related to mathematical biology, this is kind of a standard classic result. And what turns out to be is that these equations reflect a periodic behavior where one of the species depends on the other, and as one of the species is depleted, the other one grows, and then the process kind of rolls like that. So if you think of, it's also known as the predator-prey model. So if you think of the predator and prey species, if there's too many predators, they exhaust the prey, and then the predators die out, and then the prey population goes up again, and then there's enough food, and the predator population grows, and so the cycle continues. Anyway, where am I going with this? Let's think of what we saw here. These data about fish populations, thinking about chemical reactions existent or not. These data were clearly available, right? Long before either Lotka or Volterra, over the span of 20 years or so, thought about these models. And it's not unclear when the exact eureka moment happened. When exactly they developed or how the ideas crystallized. But it clearly took a while for the lack of Volterra model is that it had to germinate and the lack of Volterra model to be defined and established. So the question that I will ask today is quite simple. Can the techniques that have been developed, so machine learning techniques, accelerate the process of developing fundamental laws like these from available data? So this is where machine learning and hopefully can produce actual learning. So discover fundamental laws of nature that are general, applicable across multiple domains. So the plan for today is to talk a little bit about what a governing equation is and how we discovered them. Then we'll introduce a new framework that we developed, which is inspired from control theory, especially moving horizon estimation. I will give a summary of these results and applications to some canonical systems just to prove that the toy works. And we'll talk about some practical applications in the non-isothermal reactor dynamics, and then talk about microkinetic modeling for, again, practical situations. So what is a governing equation? Well, we'll talk about that in a minute, but what I want to also discuss here and for this audience in particular is the fact that we are not working on established problems. So there are two very well known problems in the dynamical systems area. One of them is called system identification. So what system identification is about is to say we choose a model of a convenient form. Right? This could be a neural network, it could be a Hammerstein-Wiener model, it could be linear state space, and so on. So what we need to do for that model whose form we know is to pick the parameters of that model that minimize some kind of error measure relative to the data that we have. And if you choose the model right, and you have the right data, and you do your identification properly, then you can get really good accuracy within the realm of the data set that you have. However, the extrapolation is probably not guaranteed. And there's no physical insight because you've already settled on a model form that may or may not reflect the physics of the problem. Right? The other problem is something called parameter estimation. Right? This is something you do for genetic models and so on. So here, the governing equations, the underlying equations are known, or assumed to be known, and they're assumed to reflect the physics. Obviously, you have to have substantial domain knowledge to be able to choose these equations. And then what you want to do is choose the parameters of these equations in a way that reflects or minimizes some error metric with respect to the data that you have. So these tend to extrapolate pretty good or pretty well. And they can be interpreted, they provide physical insight, but you really need a lot of domain knowledge to start with to be able to build them. So by contrast, what we're going to try to do today is fundamental learning, meaning we don't know the functional form of the model that we're looking for, and we don't know its parameters either. The expectation is that if we are able to pull this off, right, find the model, and find the parameters, this will extrapolate well, can be interpreted physically, uses fewer prior assumptions than parameter estimation. But as you will see, we'll probably pay a price for that, and that price will be in the form of computational cost. So what is a governing equation? So if we think of a physical system, let's think for now only in terms of ordinary differential equations, so not, for example, a spatially distributed process or system. So we are interested in the true dynamics like this. And these would be, the governing equation is a minimal order, so the smallest possible dimensional representation of the system dynamics, which also captures the relevant mass, energy, momentum balances. So that's what we're after. So the fact of the matter is, initially, as we start thinking of a new system that we encounter, that this piece is not known. But what we can do is we can generate data. So presumably we can change these inputs U, and then we can measure the state variables x as a function of some of these parameters. And those data would be available, obviously, most likely with some amount of noise. So what we're challenging ourselves to do is to say we have these data, the hat there denotes a measurement, and we say we want to find f or some form of f with reasonable accuracy, and we also have to balance complexity. So you could find a model that's very complex, which reflects the data pretty well, but extrapolates poorly because of what's called overfitting. So overfitting is the phenomenon or the choice of a model that has too many terms, and at that point it becomes more and more apt at reproducing the existing data, but it becomes more and more poor at going outside of the realm of the data. Right, so how do we do that? And so the idea here is to pose this question as a regression problem. This was work that has been done in the past. We will provide the references. But what we want to do is to say we have a set, or I call it the library or dictionary of basis functions. So these basis functions are functions of the states, right? And I can think of whatever could possibly be part of the model. So it could be some constant, it could be a square, it could be some trigonometric function, it could be exponential. So we want to find out what possible terms of these will be part of the model F. And so how do we do that? We use this library, this set of basic functions to assemble a set of candidate models. And these models basically are a linear combination of these basis functions. So think of xi here as a matrix, or I'm sorry, as a vector, and then you multiply it by the basis functions and you get a linear combination. So this now becomes a good candidate for applying regression techniques, right? So that is what we're looking for. We're now looking for these terms here, psi. So just to give you an example, this is what a two-dimensional set of equations would look like. Right, so this is something that has actually been proposed by the group of Brunton and Cutts not that long ago. So this was circa 2016. It has spawned a lot of research and a set of methods that people refer to as SINDI. So it's sparse identification of dynamical systems, nonlinear dynamical systems. And many of you will recognize this regression approach, right? So it's regression with regularization. So I have two regularization terms. I can use either of these. So it's L2, L1. One would be retrogression, the other is lasso. If I use both of them together, I have what's called an elastic net, right? That's something that's used commonly in machine learning techniques. So how does this apply to finding the models that we're looking for? So let's go back to the Latka-Volterra model. So this looks like a regression problem. If I look at it like this, I want to find if my outputs are the time derivative of the two states, then I want to find them as a linear combination of potential basis functions. So if you think of basis functions, here x1 is a basis function, x1 times x2 is a basis function. If you look at the plots of the time derivative as a function of x1 and x2, you see that these are nonlinear functions. But if I plot them now against x1 and x1 times x2, you see that all of a sudden I have a linear problem. Right, so finding the right bases, the right basis functions for which this becomes a linear problem is kind of central to this formulation. Okay, so for the Latka-Volterra model, again, remember what we're looking for is something that's like that. These are the coefficients that we want. So if we apply this linear regression out of the library of functions that we picked, the technique will end up finding non-zero coefficients for x1, x2, and x1 times x2 and find the right values of the coefficients. So here in the bottom, I'm plotting all the potential basis functions, but you can see that we select the right ones. The combination of those will predict the value of the time derivative of the states. So the idea works. There are, however, a number of drawbacks. And so we can think of what those are. One of them, one of the fundamental assumptions is that we assume that this linear combination of basis functions is actually a linear combination. So the model is really linear with respect to the unknown coefficients. We also assume that we can estimate the derivatives of the states from the data. Anyone who's worked with data and tried to estimate derivatives discovered that that's not always easy. Okay, so some filtering will be required because noise is present and so on. So this is challenging, especially when some of the states are not measured. And then these are strong formulations, right? So we evaluate the governing equations on the measurement data. So the noise will not help. And then for any kind of regression approach, collinearity in these basis functions will also be an issue. Okay, so this is what's been done. That's kind of the background that I wanted to discuss. The idea that we're going to borrow from this work and try to bypass these disadvantages is that you can learn from a library of basis functions, you can learn a fundamental governing equation model. So what did we do, or rather what did Fernando do, is we borrowed from the concept of moving horizon estimation. So for those of you who are not familiar with this, it's sort of standard practice in model predictive control. And what you try to do through moving horizon estimation is to say, I have a model, I'm going to look at some past data and inputs to the system, and I will try to predict the state of the system at the current point, or estimate the state of the system at the current time. Right? So it's not a prediction necessarily, you can do prediction too, but the idea is to say, I'll take past data in my model, and I will make sure that I estimate the state of the system at this point in time. So this translates into, now you don't have the model, but you try to find that model. And what we try to do is to break up the data that we have into chunks, right? These are time series data, these are dynamical systems. What we want to do is we take a chunk of data, we say, I have my model, which is in this form of coefficient times a coefficient vector or matrix coefficients times a matrix of basis functions. What I'm trying to do is minimize the difference between what my model predicts and the data that I have, perhaps with some regularization to eliminate some of the terms from the library. And I'm going to do this over kind of a moving horizon. So what I have is I will do an estimate for this chunk of data. And then what I'm going to do is I'm going to shift my horizon over the next chunk of data and so on. So with that, what I can get is a sequence of estimates of the coefficients of the basis functions. So what this tells me is that I can do a lot better than what I've done with linear regression, because now I can calculate some statistics on this sequence of estimates. So for example, I can find the coefficient of variation. So that's the standard deviation over the mean. And then there will be some of the coefficients that have a very high coefficient of variation. That means I have low confidence in those coefficients. And that tells me that perhaps those terms in the library, the basis functions, are used to fit noise. Right? They're not helping my model. I can prune them out. So this is a good way of getting rid of pieces of your library and eliminating the overfitting problem. So there's, of course, a whole process for implementing this idea, right? The concept is fairly straightforward, but just like with every data-driven approach, especially if you work with large-scale data sets, there's a number of preparatory steps that need to be taken. So data smoothing is something that we do in order to implement this idea. keep in mind that this problem that we're solving here is a nonlinear optimization problem. So anything you can do to help will be good. So one of them is data smoothing. The other thing is we do perform a causality test between the basis functions and outputs. And what that tells us is if I find the values of basis functions, I can test them to see how much they impact on one of the outputs or predictions of the system. So if I predict better without the basis function, or the prediction without one of the basis functions is not affected relative to the prediction or the quality of prediction with that basis function, then I can eliminate those components of the model, right? So all of this preliminary work is also very helpful. The other thing that we do is we actually do ordinary least squares, just like I showed earlier, in order to get to initial estimates for the parameter values. So that's something that helps. Again, you're in a nonlinear optimization setting, so good initial guesses are very helpful. Okay, so the way we solve this problem, again, I'm not going to go through the details, is we have to solve a nonlinear dynamic optimization. We use orthogonal collocation on finite elements. And so we adopt what's called a simultaneous solution. Proving the library based on statistical arguments. Again, I'll reiterate the fact that we use the coefficient of variation as one of the criteria, and we use a threshold for this coefficient of variation. So as soon as the CV for a specific parameters goes above the threshold, then we'll prune that basis function from and then how does this end? Well, it can end in several ways. One is that after a number of these iterations, there's no more change in the coefficients of the basis function. So we've kind of landed on a model that doesn't change anymore, no matter what data we throw at it. Okay, that's done. The other one is, well, we're out of data. So that can also happen. And in that case, we also declare the procedure to be terminated. Although in the second case, this data are exhausted, doesn't happen very often, because you can imagine that you can apply this process to different chunks of data, right? So you can move through the horizon, or you can expand or contract the time span of the data that you consider. So all of those can help you basically stretch out the data that you have quite a bit. And then we can do validation. So the validation we can do by integrating in time the model that we get, and then comparing the results with what we have in the data. So how does this work? It works for the Baldea system. The discovery has worked quite well. And there's a number of things that I want to point out in these plots that are relevant to the way the discovery process works. So here we're looking at iterations. And you can see that the model always starts with a pretty high number of terms, right? So we start the library with 15 or so potential basis functions. And as the iterations progress, the number of terms retained in the model drops to the 2 that we, or it's actually 3 that we expect to keep in the Baldea model. Okay, so this works reasonably well. And then you can see here that we do a number. So we have about 30 iterations. There's a number of thresholding steps that we do there in order to do pruning of the library. And you can see that this is the coefficient of variation for the basis function. So the basis functions that are kept in the model that I'll refer to as active will have a pretty low CV, whereas the ones that I get rid of are going to have a CV that's higher than the threshold that I set. You can see here that we can look at the influence of the model or the data noise on the prediction error for a model that we discovered. And as you expect, the more noise you add to the data, the higher the prediction error is going to be. So no surprise there, but we wanted to test and make sure that nevertheless that's true. And then you can see here that for the data that we have, which are fairly noisy, the black line is the true periodic orbit for this in the phase plane for the form of the model that we have, and then the discovered model is actually overlapping that perfectly. So this works for a very simple Baldea system. It also turned out to work for a number of other canonical nonlinear systems. So van der Pol oscillator, again, if you took a class of nonlinear systems, I'm sure you've encountered this. Why is it different from the Baldea? It's different because it's stiff, right? So the two states move at different rates. And so that always creates a problem as far as data-driven approaches and any kind of any approach, actually. And you can see that the same story happens here. So we start off with a pretty overfitted model, and through our pruning process, we can get it down to the correct number of parameters or terms in the governing equations. The oscillator is a periodic chemical system. Why is this interesting? Well, it has this pesky constant here, which you wouldn't be able to discover with a linear regression approach. And we're able to catch that. And then finally, the Lorentz equations, if you're not familiar with these, they're the original weather model. So Edward Lorenz is trying to simulate weather. And then in the 60s, he was out of computing power. He stopped the simulation, saved the current state of the system, and then restarted the next day. And it took a completely different orbit. So with 3 states in a nonlinear system, you can see the advent of what's called chaos, right? So this is actually a chaotic system, and we're able to pick that up as well. How do we compare with Cindy? These plots are, again, referring back to the canonical nonlinear systems that I discussed earlier. The way to read these plots is to say the line, the vertical line, shows the right number of terms in the model, and the y-axis is the prediction error. And we compared our approach to a bunch of the variants of Cindy. So there's a weak Cindy, there was a ensemble Cindy that kind of came out after the original Cindy idea was published. So those are all available. The codes are available. We used whatever original codes were published. And then the diamond, the red diamond is our work. The best solution that you can get is low in error and right on the line, right? So you found the right model structure and your parameters are good enough to give you low error values. And you can see that systematically our approach lands on that spot, right? So the low error right on the line in terms of the structure of the model. So we did pretty well compared to what would be the direct competition of this idea. Okay, so what have we learned? Nothing. These are things that we already knew. They've been discovered, so we rediscovered things that were discovered 100 plus or less than 100 in the case of the Lorentz equations and thus later. But the things that we discovered we already know. So the question is, where do we go with this? How can we apply this to practical things? And the practical thing that we had in mind was looking at reacting systems. Why are reacting systems different? They're fundamentally different from what we talked about earlier. And if you think of the governing equation, now you have a parameter here, which appears in the actual basis function. So you're no longer, you're violating the assumption that the governing equations are a linear function of their parameters. And if you think of reacting systems, I don't know how many of you are chemical engineers. Most? Yeah. Okay. So you've seen the CSTR model, right? What happens here is if you write the mass and energy balances, there is a reaction rate expression. In the reaction rate, there is a exponential term that reflects the dependence of the reaction rate on temperature. In that term, there is something called the activation energy, which is a parameter, right? It's independent of anything. It's just a parameter for a reaction and the catalyst, perhaps. But that is now part of that exponential. So this exponential basis function is no longer independent of parameters. It actually has a parameter within that exponential. And that basically throws everything that we had done as far as linear regression goes out the window. So we have to rethink how this would work, right? So the basis functions now have a nonlinear parameterization. How do we find that? So we have to really update our workflow for dealing with these reaction systems. So I'll argue that none of the Cindy tools can work for this. Right? So what we did, however, works. It needs a little bit of rethinking. So clearly, for those parameters that appear in the nonlinear fashion in the basis functions, we have to find good initial guesses. And so that's crucial. And the way we do that is to use correlation analysis. So we find the correlation coefficient between the estimated derivative and the basis functions. We know what the basis function looks like. It's an exponential. And we want to find, for a range of activation energies, so to speak, we find a value that gives you the best correlation between that basis function and the rate of change of temperature and composition. So you can see here that this site, for a simple CSTR, the idea works quite well. So here we tried, so this C is actually EA over RT. And you can see that the correlation is either minimal or maximal at a value that is actually very close to the true value of the parameter. Right? So this helps us find good initial guesses for the parameters that show up in the basis functions. So for the non-isothermal CSTR, we did the discovery. Again, we haven't learned anything new because we know the model of a CSTR. But nevertheless, we learned that our technique works. And I'll show you these plots that will come back and again. On the left-hand side, you see the model structure, right? So it's the number of coefficients in the model. And on the right-hand side, you're going to see the error. How does the learning process work? You start with a model that's very complex and has low error. Okay, that's a bad sign. It's a bad sign because it reflects the fact that you're overfitting. You're using an overly complex model to reflect the data that you have. And then as the learning iterations progress, you can see that the complexity of the model drops, and it drops down to the number of terms that you actually want to have in your model. At the same time, the error drops. So that means that you found the right model structure and the right model parameters for predicting your data. And you can see here that the estimated coefficient, so this E to C over T, actually converges to the correct value in both the composition and so the material and energy balance. And you can see here that we started with a fairly complex set of basis functions, which included the inverse of concentration, which you can sometimes have, like for example, a combustion of methane, which is obviously not the case here, but certainly we tried to cover all bases as far as the starting point for the model structure. So this also works for, in terms of validation, what we did was to test the estimates for normality, and then estimate a covariance matrix, and then use that to generate Monte Carlo samples for the values of the parameters, and then simulate the reactor forward in time to see if we can match the data. And you see that the match is actually between the discovered and the existing data is actually quite good. Obviously, there's going to be quite a bit of error around those values as you consider more and more Monte Carlo scenarios. So this was encouraging. I want to mention in passing that we applied these ideas to a system with an excitation signal. The previous CSTR that I showed is actually itself periodic, so it generates these data that cover quite a bit of the operating range. Here, what we did was to change the coolant flow rate, we changed the system temperature, which would be what you'd consider a system identification experiment. And in this case too, we were able to find the right coefficients in all the terms. This also works for batch reactors. This is interesting because the batch data can become one of the training periods. So you can take, let's say you have fewer batches, but you can iterate between them and use that as your time horizon for applying the learning procedure. And you can see within the same plotting framework that the model structure is identified correctly, and then the error for prediction also goes down. So this works for batch processes as well. Okay, so where did we apply this at scale? Which ultimately is what the question should be, right? You take a technique, it should, especially as far as data-driven techniques go, you should be able to make them scale. So we did this for microkinetic models. So microkinetic modeling is used to elucidate complex reactions, and what you do is you postulate a number of intermediates and reaction steps, and then what you want to do is to predict the outcomes of reactions, depending on the substrate that you choose and the reactants that you choose. So these have a very high computational complexity. These models are very stiff because the intermediate reactions can happen at vastly different rates. And so identifying out of a potential set of steps that you postulate, and there's now mechanisms for automatically generating these steps for different reaction families. So the key is to say, all right, I have a number of potential reaction steps. Which ones are the ones that best explain my data? What is the fundamental model for the reaction that I am interested in? And I would say that a lot of the work on microkinetic modeling has focused on isothermal reactions for networks, and with only measurable species. And this is where the collaboration with Linda Brotbell's group came into play. This is a sort of key work that we did, because we recognized in talking to Linda that, in fact, these mechanisms are amenable to be represented as a library of basis functions, and then those basis functions would in fact then be used to create a microkinetic model that's minimal order and of interest to us. So how do we set up a prototype reaction network model? Just to give you an example, is we create a number of candidate elementary reaction steps. So let's see here, what we'd want is really A plus B goes to C, right? Which is the most studied reaction in the world. That was a joke. It's not true. So but let's say A plus B becomes an absorbed, or A and B become an absorbed species. This would be a reaction site. And then they go to C and free up two sites. You can have A goes plus A plus two sites becomes absorbed on two sites, and so on. So you can generate any number of these. The question is, which ones are the actual true ones? So there's a number of ingredients that you need in order to elucidate this question. One of them is the reaction rate equation. So these follow the Arrhenius law. And then there are some mechanisms for estimating some of the parameters, right? So you can estimate, using transition state theory, you can estimate a pre-exponential factor, and then Evans-Polanyi relations that presume that the activation energy kind of can be predicted for reaction families, would also give you an estimate of EA, right? So the activation energy. Then you couple this with reaction design equations, which reflect the way you run your experiments, either in batch or in a continuous process, and then you can write the material balances for that reactor. So all of a sudden, this starts to look like the problem that we've defined earlier. So you have a dynamical system that's high dimensional. It has a number of terms, right, which would be these intermediate reactions. And then we ask the question, how can we prune these terms? How can we get rid of some of the reaction steps that are actually not occurring in practice? So the key questions that I'm going to ask, one of them is discovery, right? Discovering the governing equations. So given a set of composition time series data, and a set of candidate reactions. So these elementary reactions. What is the set of elementary reactions that best explains the data in the experiments? The other one is network reduction. So it's of high interest to come up with lower dimensional models that still explain the data within some degree of accuracy that we define, but are smaller, so they have fewer states, and therefore much easier to work. Okay, so these are the two questions that we're going to try to answer. So there are two types of scenarios we can think of here. There's single temperature, so everything occurs at one temperature. And you can think of multiple temperature, which is just an extension of this problem. So in the single temperature scenario, we try to minimize an error that's defined as the difference between predicted and measured compositions, subject to the reaction rate and reactor design equations. And then for the multiple temperatures, you add the Arrhenius equation, so the temperature dependence of the reaction rate, and you do this over the whole set of temperatures that you have. So it's just a larger problem and more complex. So what we did was to develop a heuristic that actually decomposes the multiple temperature problem into a sequence of these single temperature problems, which makes a lot of physical sense. And then we can alternate with pruning reaction steps. So how does this work for the prototype reaction network? So in this case, we know when we generated the data that these are the actual elementary reaction steps. These are spurious steps that we started off with, but we know they're not there. So the question is, can we get rid of these? Right, and as it turns out, we started off, there's 14 potential reactions, including the forward and reverse reactions. And this is, again, the same type of plot that you've seen before. So we start off with all the reactions, and you can see that as we proceed to the learning iterations, the number of reactions goes down to the ones we actually have here, which is 5. And then the error also tends to decrease. Okay, so we are, in fact, able to boil it down to the fundamental reactions that are occurring in this system, right? And then the reaction rate constants, on average, based on our predictions, actually land on the true values. So if we start pruning beyond this here, then we'll violate conservation and mass, and we really shouldn't be doing that. Okay. If we are to simulate the system that we've learned, actually overlaps perfectly with the data that we generated. So this works well for the small system. Now the key question is, does it work for a real problem? So the real problem that we're looking at here is something that came as part of another project where Linda and I were involved, which was called C-Star. And it had to do with upgrading shale gas feedstocks. So things that come with natural gas but are not methane into heavier oligomers, right? So something that would be in the gasoline range. So if you could get to propylene, the question is if you can get into the kind of C6 type compounds, which could be used for gasoline. And the use here case was unburned zeolite. And so you can see that there are a number of potential pathways, right? So there's these hydride shifts that can go that way, or there's a methyl shift. And what we did was to say, we're going to get a number of data. These data are actually from simulations at this point, where only the hydride shift is present. We're going to assume that the methyl shift also occurs and see if we can discern the fact that this is actually not happening from the data that we have. And so the families of reactions that have, there's actually 31 reactions. I will say that the literature that we've seen that focuses on discerning models of this type, there's a group of Medford at Georgia Tech, there's a few others. They really just, the biggest number they've been able to go is 5. Right now you're looking at 31 potential elementary reaction steps, so it's a big factor over what the current literature affords. And you can see, looking at the same type of plot, right, the model structure versus iterations and then error versus iteration, we see the same phenomenon. So we're able to prune the library basis functions down to the 19 that were actually used. So the methyl shift ones are gone. And we land on the correct values of the rate constants. So we are relatively constant in terms of NSE after about 30% of the elementary reactions are common. But then we can decrease a little bit further. So how do we do this further? So now if we want to eliminate more reactions staying within some measure of precision for our predictions, we can apply regularization, and we apply the regularization to the pre-exponential factor. So regularization means it penalizes every time or every pre-exponential factor that's non-zero. So we want to drive the pre-exponential factor to zero, meaning we eliminate reaction steps. And you can see here that if we look at model structure versus error, there's kind of a sweet spot here. So the error starts going up after we're down to about 12 equations in the model. So down from 19 to 12, it's about a 30% reduction again. And we're able to get down to actually 11 reactions that tend to eliminate surface intermediates. So you lump the reactions, which is something that you do in practice anyway. So how do we validate this reduced order model? Well, we simulate the model against the data that we have. So this would be the training data on the right, the discovered model on the left, and we're looking at the gas phase species. So these are partial pressures, and then we look at side coverage, which is the adsorbed species. We predict the gas phase dynamics pretty well. We cannot resolve very well the surface intermediates, which is typical for lumped models. I would point out that this model has very strong extrapolation capability. So the data that we have are in this temperature range around 450 plus minus, I believe, 10 degrees. But these plots show R squared here and the slope of the parity plot in yellow for the different species. You can see that the parity plot stays close to 1 for a very large range of temperatures outside of the temperature range of the data. And the same R squared is also close to 1. So this shows that the model extrapolates really well. Okay, so to conclude, I want to point out that there's a significant difference between reproducing and understanding, right? This has been a challenge in education in general. Machine learning is great for the former. The question is, how do we push it towards the latter? The fundamental learning is something that we want to lead to general principles that are transferable and applicable to all systems that meet certain conditions. So machine learning can lead to fundamental learning. I'd say the success is still limited to small scale systems, much larger than what others have done, but still fairly small. I'd say yes and no to no new discoveries. I think we can discover, we're ready to discover new things as soon as the data become available as far as reaction engineering goes. I'd say just like any other data-driven approach, a lot of prep work is involved in preparing the data. And there's no one-size-fits-all solution. So when you hear the term hyperparameter tuning, there's a lot of trial and error in applying machine learning methods. I think this sort of falls in that category as well. Okay, so what we want to do is synchronize this with a design of experiments. I think we are on our way to come up with a theory of discoverability of systems and tying that to what we call observability in systems and control theory. Obviously, we do want to do this at scale. All of this is available on GitHub. There's been a number of downloads of this. It's been pretty successful. There's also a couple of forks of it, and I'm curious what people are doing. I haven't quite found out yet. And I want to thank my entire group and our support from NSF and Aaron Capella's program for Fernando. And then Mark Stouthair and Steve Wright have been really instrumental in distilling these ideas in the early stages. So with that, thank you.